All right, let's go ahead and get started. Welcome, Robotics 311. We're getting pretty far in this class. It's kind of exciting. Today we're going to review IMUs, kind of the stuff we talked about last time, and encoders. We're going to finish with encoders, talk about digital communication, and I'm hoping we can get all the way to omni wheels for the quiz. We might not get to omni wheels, but hopefully we do. Homework 4 will be posted today, I promise. Midterm exam is 2 weeks from today. Has your homework 2 been returned to you and graded?
I don't think so.
Even got sick right now, so I was waiting on him to reply to me on that. So hopefully all soon. He got sick this week, so he's not here today. And I don't think he did office hours yesterday. Did he do office hours?
I got canceled.
Yeah, so he's not feeling well. So hopefully he feels better and is back soon. And Senthar's gone. He's back in India. He'll be back soon, but he's not here either. So right this week, it's just me. Okay. Any questions about class stuff? We're going to continue today. This kind of data acquisition, sensing, and mechatronics. This kind of last section before we get to control. For sensing, we talk about different types of sensors. We talk specifically about encoders and IMU. Some sort of physical process, convert that to a digital value. We went through a few of those. IMUs are often described by kind of the different number of axes or degrees of freedom they have. The IMU that you guys have, do you know what it is? So how many axes does your IMU have? 6. How'd you know that? What does it not have? Magnetometer. Do you know the part number for the version of this IMU that does have a magnetometer? It's 9260. Okay, so yeah, they make a version of this IMU that has a magnetometer, but you guys aren't using that. That's right. And then these are other types of sensors. Vision and LiDAR, something that you might see commonly in robotics, but we won't talk about. Same thing with force or torque sensing. Really important in robotics. We won't talk about. Not so important in like hobbyist robotics. Force and torque sensing is more frequently a concern for higher performance robotics. We talked a little about different IMUs and how they internally take information about position and orientation. That comes as linear acceleration and angular velocity. And they take that information and fuse it. And we get that information kind of directly from the IMU and its internal motion processing engine. Inside the IMU is a small flexing structure that's used to measure acceleration. How they work, these are MEMS structures. It measures net force, which does not separate gravity. A big part of working with IMUs is understanding how to separate the effect of a gravitational acceleration from actual motion. These systems are kind of inherently low pass because they're a structure that is typically vibrating. They have some natural frequency, but they're typically much higher than the things we want. Frequencies we want, they go up to about 500 hertz. This one's just a couple tables that kind of showed you some examples of different types of error and how it might affect the integration to position. This is kind of bias error kind of inherent in the sensor. This would be reported on a data sheet, typically with the name bias error. This is mounting and misalignment error, so that would be an issue of us installing it incorrectly, or the sensor inside its structure is not perfectly flat. And then also there's kind of like gyroscopic or different random walks. Those will also be described typically with that wording, random walk. We talked about how random walks come about. Well, can someone tell me, refresh our memory? How did random walks come about, or what? Why is it a random walk? Why is it random? Or where did it come from? Anything close to what we talked about?
You know, like the noise that's generated from the different measurements, and then kind of like take like a Gaussian distribution and we'll plot the error of around 0.
Yeah, that's right. So it had to do with the noise on it. And if we model that noise as sampled from a Gaussian that has mean 0, has some standard deviation. If we collected for an infinite amount of time, it would have a zero mean. If you integrate that over time, that integration will accumulate and it'll just drift based on the random sampling. Good, okay. This talks about our MPU 6050 and its internal DMP. This is like a huge help for us. If we didn't have access to this inside this IMU, this project wouldn't work. So this is like a critical part of making the project work. It uses internally, it uses complementary or common filters to fuse that information together. In your system, you guys realize that all the communication and interaction with the IMU has been abstracted from you. So we've taken care of that, and although I want you to know about it, you don't actually have to do any of it. Does that make sense? You could, like you guys are capable of it, and it would be within the scope of this class. It just takes a lot of time, and I think it's easier if we just abstract it. We look at that API though. I think that's kind of like worth looking at. If you guys haven't gone through that, just looking at it, they're not always that sophisticated, but that one is. Okay, when we talked about different types of encoders and measured groups being relative or absolute, encoders measure angular motion, usually through an optical or magnetic setup. We talked about optical and magnetic. Hall effect is another type that's really typically low resolution. We won't talk about that. And then potentiometers are not robust, so they're just not a good way to do it, but you do see it sometimes. They're also analog, which would be more challenging for us to implement. Why would an analog system be more challenging? So if I gave you the option, here's an encoder, because you have an analog option or a digital option, and let's say you're creating this ballbot setup. Which would you choose? Yeah, and why?
Digital, because you have more options of like where to stop it. That makes sense because for analog you only have like 0 and 1, so like.
Analog, so if it was analog, maybe we map that voltage to like a triangle, so every angle it goes around makes the voltage go up. So we could output that as an analog voltage and then sample that with a digital to analog converter, but it would end up being just more complicated, like more inconvenient. We'd have to interface, you'd still have to get a driver, so a software file that interfaces with your analog to digital converter, so you wouldn't get around having a software driver. So it's just easier, if we're going to create a software driver, it's just easier to write one for the sensor itself, and then you don't have to worry about an ADC. So that's kind of like, it's more a convenience thing, and now it's, I think, more common that sensors are digital anyways. Okay, we talked about these two different types. Optical encoders, basically like shine light through a laser cut disc, or sometimes a etched piece of glass or metal. The patterns on the disc create these different kind of pulse trains that can be used to tell angular motion. We talked a little bit about this digital opposite signal called not. So this would be like A and A not. Your system doesn't have this, so you don't need to worry about it, but it's common. You would definitely see it if you were looking or building robots, especially like more sophisticated robots that care more about their motion positioning. So the approach for this, high resolution, resistant magnetic interference, low cost, they're everywhere. If you buy a motor, these just come on them oftentimes. Magnetic encoders I think are better, but you have to implement them yourself generally. So use a small magnet that's diametrically magnetized and it just senses the magnetic field. It works really well, it's absolute. That's what's great about it. So high resolution, absolute, low cost, simple, but you just have to add it yourself. So you have to typically add, like a motor wouldn't come with that on it, yeah.
Is it absolute like relative to like the very first time you use it, or relative to like some global like coordinate or something?
Since it's a magnet and a magnetic sensor, it's global.
So like what would the like actual output of like position be in that case? Like
it would be a number.
Well, like I guess can you then convert that to some like, I don't know, like longitude and latitude or something, or like how would you, because you're saying it's
yeah, everything ends up being an angle. So this is a 14-bit encoder, So it's gonna map whatever that is, 16,000 to 0 to 360 degrees. So every single one of those bits will map around the circle. Then whenever it senses, it's gonna look at where it is and provide that value to you.
So is that angle though like relative to like some spot on like
It's relative so that sensor senses magnetic field, that's a magnet that then is fixed to one of the parts.
like the magnetic field is like of like gravity and like the earth or
No, you're sensing the magnetic field from that magnet. The magnetic field from Earth is in there, but probably like 10 to 100,000 times weaker is my guess.
okay.
Somewhere, magnetic field's about half of the Earth, about half of Gauss. I think that's gonna be Gauss, yeah.
That angle is relative to like global north. Is that no?
No, it's just relative to how this magnet is positioned.
So how is that then like absolute versus relative?
It's absolute because whenever you boot it up, it will always return to you the same angle, no matter what. If it were relative, it would wake up thinking it's at 0, and it would only know relative changes from that 0 point. This always tells you where you are on the circle the same way every time.
So it's absolute as in it tells you the angle, but it's not absolute. It doesn't tell you the count of rotations that it's done.
It wouldn't tell you the count of rotations that it's done, so that you'd have to do that on your own, which is typically done, generally always. So you can always tell, if you see a giant, if you look at a diff, you look at your last value and your current value, and you see a huge spike, either positive or negative, that means you made a loop. So you just add 360 to your degrees generally. Yeah, so that's typically always done.
And is the magnetometer usually better for just getting velocities or like for absolute position or for like getting position too?
It's good for getting positions. I mean, for velocities, it would be the same. Like the only time the encoder really comes up into velocity measurements is if you have to numerically differentiate it. So if you're sampling, imagine you're sampling that encoder really fast. Now also imagine you have a low number of counts per revolution, so a low number of digital values per cycle. If you think about what could happen, you would end up with basically like a bunch of the same values, then one encoder value different, then a bunch of those values. So you'd end up with velocity signals that just look noise because of the quantization that it would exist. Good questions. Other questions? Awesome. So hopefully that helps us understand a little bit about relative and absolute. We're going to talk more about that now. Okay, so this is new stuff. Talk about quadrature decoding. So this is how we know how to sense velocity direction when we use quadrature encoders, which are the most common. Quadrature encoders are of type of relative encoder. So they're two relative encoders used together. So let's write this down. Many motors use relative encoders, including yours. Your motors have relative encoders. A key question is, the direction of angular velocity this is accomplished using quadrature decoding. Quadrature decoding is using two encoders that are positioned a small phase shift from each other. Usually 90 degrees. So then if we do this, so we have an A and a B signal now. One is phase shifted a tiny amount. Now we can just look at which signal rises first. Now we have an understanding of velocity. The signal that rises first is used to know direction. indexing is used to get absolute position from a relative encoder. So this is common, but also like doesn't always exist. But it would be 1 mark. So this is an example of an encoder wheel where it's showing the 2 different A and B lines of your encoders plus the index mark. So it means it's going to go around and then give you a pulse. So now you can at least get to within 1 rotation. It gets tricky like when you have many rotations on the output. You have many index marks to track, but this works. Like you can figure out where you are with an index mark. They often provide them. So which direction is this wheel spinning? This wheel. We can say that white is when it's on. Yeah.
Counterclockwise.
Counterclockwise. Yep. How'd you know that?
Okay, signals rising first.
Yeah, so A is leading. So if white is on, A has to go first. So if we look at kind of a radial position, A tracks first if it's going counterclockwise. Does that make sense? Yeah.
Theoretically, we're turning it like clockwise. I don't know. Maybe I'm not like fully understanding just like the setup, but like wouldn't it technically like hit like the B before because like there's like that space where A is not on it, and then like.
If it changed direction, then
Oh,
B,
wait,
B
then-
would lead A,
Oh, okay. So.
which is that's the idea.
Yeah, okay, that makes sense.
Index mark. Okay. This information is usually described with your motor. So encoder information, because it typically comes on, even though it's usually a separate product, oftentimes having its separate product literature, since it's assembled with a motor, they're usually bought at one time and they're usually described in the same place. So encoders are typically described by their counts or revolution. When digital negatives are used, so you see those not signals, A naught and B naught, then you can sometimes get a multiplier on your number of counts. So when digital negatives are used, the encoder counts can be multiplied. So by 4x or something. Sometimes you see this, but your system doesn't have it. Encoders are often discussed and purchased with a motor. And so for your system, it's described in the motor's data sheet. So here's a little task. What I want you to do is not get this from Canvas. Find this on your own. So find this on your own. This, you need to find your motor's data sheet. Like imagine you're trying to, remember when you were plugging your encoder in and we were telling you which way to orient it? That's because we went through the pinout of that, pinout is the mapping of the pins of that connector and figured out what goes where. And so what I want you to do is kind of practice doing that. This is definitely like the kind of thing you guys have to do. So I want you to track down this data sheet and find the pinout, color pinout for that encoder plug. And then show it to me, yeah.
What are the first 2 words on encoders are often discussed?
Discussed. Discussed and purchased.
Thank you.
Discussed and purchased. Okay, so yeah, I want you to track this thing down. And if you notice on this Pololu website, this is from the Pololu website, it shows 64 count per revolution encoder. Now, if you look at this name, you guys look at this 1 second, before you go back to this task. 70-to-1 metal gear motor, that's telling its dimensions, 12 volts, 64 counts per revolution encoder, and helical pinion. My guess is before this class, that would have been like maybe difficult to decipher. My hope is that now if you read that, you kind of know almost everything it's saying, or certainly like where that information is, what that's guiding you to, and kind of where it fits in the robot design process. So, you know, hopefully you feel that way. I feel that way. I feel like you could do that. You should be able to make sense of that name. Do you want to talk through it, or do you guys track it?
That's just referring to the IMUs during the transmission ratio, right?
Yeah, transmission ratio, those are dimensions. 12 volt means it's going to operate in its useful range up to like the 12 volt winding voltage. 64 counts per revolution, that's how many encoder ticks per revolution on the motor. And then helical pinion just means that that's how the internal little transmission setup. It's using a helical pinion on it. That's it. Did you guys find this information? Who has not found it? Okay. Yeah, find it. Everybody find it? Okay, it should look something like this. So if you found it, this is what you should be seeing. So what this is telling you is like red, motor power. Black is going to be motor ground, so that's your winding voltage. So those are the two leads that actually provide the motor's voltage. Green is encoder ground. Encoder power is blue, so there's something has to power the circuitry in the encoder. And then you have A and B. They're just your two pulse strengths from your relative optical encoder. Cool, huh? If you guys were ever trying to find any information about any sensor or component, where would it be located? In its data sheet. And then where can you find data sheets?
Manufacturing websites.
Yeah, online. You can find them all. They're everywhere. So like you can always, there's always a data sheet for something, and it contains super helpful information, and you might have to just track it down online. That always works. I've never been able to not find a data sheet. Okay. Awesome. Tons of time. Now we're going to go into communication. Before we do that, I wanted to like remind you where we are in the process. So this is kind of the first part of the class, the first third. We talked about speccing, how do we set up the problem, how do we understand what components we need to buy in order to build this thing and make it feasible. Talk about geometry component, how do we build a machine, lay it out, geometric considerations, how do we model it in SolidWorks, create the file types we need. Manufacturing, we did all these different rapid prototyping tools, laser cutter, water jet, 3D printer, talked about sensing, a few different sensors, specifically the ones you guys are going to use, and then we have like a few more things to discuss. But this is sort of generally the flow that goes on. This order is a little bit different just because of the labs. We kind of had that kind of constrained what we kind of teach you when. Like wheels should probably have been kind of like up here. But in general, like I hope what you're seeing is sort of a framework for how to build robots and make them move. That's the purpose of this class. So like part of it is like upfront, speccing and MATLAB and paper and pencil calculations. Part of it is like actually at the computer, making solid model files. And then this is kind of thoughtfulness and then hands-on work. So today we're going to go over hopefully these two things. And there might be some other modules added in as we go. But this is kind of where I see how this whole class is coming together. And our system doesn't use SPI or Mecanum wheels, but we're gonna learn those because they're good to know. Okay, so let's take a second, look at our high level control of our system structure. So when you're building a robot, you have to make a choice, what's gonna be the intelligence? It's gonna look at the sensor data, make some decisions. You have to make that decision, which might have to do with what programming language do you like to program in? What have you used before? Those kind of practical considerations. How much computation do you need? What other peripherals do you need? But at some point, you have to choose a platform for what I'm calling high level control. So something making the decisions about what to do. How is that different than low level? What's doing low level control? What do you think in this system? Yeah, the Pico would be doing our low level control. Raspberry Pi is doing our high level control. Okay, and that can take on many forms. Anybody have any ideas for high level controllers they've seen or used in the past? Arduino. How about other ones?
Any microcontroller?
What?
Any microcontroller?
Yeah, what's your favorite? Do you have one you use?
It's just kind of a subset of the Arduino, the ESP8266.
Okay, I'll put pick.
Yeah.
Also BeagleBones. Do you guys know BeagleBones? That's a real common one. Laptops. It doesn't have to be one of these really small ones. It can be a straight up laptop. What's up? Jetson? Is that what someone said? Yeah, Jetson's another one. What's the Jetson designed for specifically?
GPU computation.
Yeah, machine learning, linear algebra. Okay, great. Yeah, so there's lots of options for different high-level controllers. We're going to use a Raspberry Pi. And I'd say Raspberry Pis are common choices for high-level control. Why do you think that Raspberry Pi is often used? There's two main things I think go into it. Yeah.
It used to be really cheap.
Yeah, it used to be really cheap. So really cheap is one of them. Till their supply went to basically zero. So they used to be really affordable. They were $40 generally. And what's the other reason? That's one. What's the second reason? Yeah.
They have more library capabilities.
There's a huge community that create everything. Not just creating libraries, which is hugely important, and there's a lot more library availability, but there's a community of people asking questions and people answering questions. So if you're having an issue, you can probably find an answer to it. That's kind of unique to the Raspberry Pi, at least it has been. Maybe BeagleBone, I'd say, is right behind it, but it's, I'd say, far behind it in terms of online support community. Okay, so we are using a Raspberry Pi. It's a common choice for controller. It has an extensive online compute community, which helps build repositories and all sorts of things. Choosing sensors. Communication or comms. And high-level control. Often is decided together based on what you've used. Mostly based on what you know. You guys read this? Let me know if you can't. So when you're making this choice, you're often thinking okay, what programming language do I like? Okay, I like Python. Do I need wireless networking capabilities? Do I want to be able to SSH into it from my laptop? So we use Raspberry Pis because it enables these things. We have tons of wireless networking infrastructure and capability. It runs fast. It doesn't run what's called real time, which means you can strictly control the speed at which it runs, but it runs pretty close. If you ever run your code and you'll see the ballbot, it ends up outputting its loop timing. When you exit, you're going to see that it's really, really close to real time. but it's not real time. So that's one of its drawbacks, but every time we kind of make a choice about what system to use, we always choose Raspberry Pi, at least in my group. So our system is 3 encoders interfacing with the Raspberry Pi Pico, 1 IMU interfacing with the Pico, the Raspberry Pi communicating with the Pico. What do these signals look like? We know?
There are like 2 pulses with like a difference in phase.
Yeah, we're gonna say they're AB pulses. So the Raspberry Pi Pico could actually watch those AB pulses and count them. And that's a special function that the Raspberry Pi Pico can do. A regular Raspberry Pi couldn't do that. It would have to have a dedicated chip that did that on its own, but the Pico can do it. So it's actually receiving these AB pulses from those encoders and it's counting them. And then it's communicating with an IMU, the MPU 6050. It's communicating over a bus called I2C. And this communication, I think it's done over serial, definitely. I think it's RS-232. So this is a communication structure that was made by people at Michigan Robotics. So this is defined by them, I think built on some libraries that exist. You guys won't have to worry about this as we hand it to you. And you guys can use it in the future. We're working on making all this open source. So you should have access to all of this in the future if you ever wanted to build other things. This I2C library is freely available. I showed you the Python version of it. The version of it that's running on this is written in C. So the Pico runs a C program. I think it also can run Python, but we have everything written in C. And then it's just counting and receiving the AB pulses. That's kind of our entire system. Any questions about that? Okay. Before we kind of get further into talking about digital communication, I think I want to just refresh quickly like digital numbering and numbering structure. So a review of base 10 numbers. So digital numbers provided in zeros and ones. Somebody tell me like the number 4951 base 10 is something times 10 to the third plus, can you fill these in? Oops, okay, so, oh, look at that. Something times 10 to the second. That's something times 10 to the first. Can you fill these in? The first one's 4, 9, 5, 1. So you guys kind of see how we structure a base 10 number. Awesome. Good. And binary, obviously, it doesn't do that, it's base 2. And we're going to talk quickly about another type of numbering structure that's base 16. So the most common formats that you'll see in robotics or in mechatronics are binary, decimal, obviously, then binary, and hexadecimal. Binary is base 2. And it just consists of 0 and 1. Hexadecimal is base 16. Who knows the yeah, what is it? What?
Is it 0 to 9 and A to F?
Yeah, 0, 9, A through F. That's right. Okay. So we can convert numbers to base 2 for binary, base 16 for hexadecimal. Why do you think, why is binary helpful? Why was binary created? Yeah.
Because at the end of the day, like the computer can only acknowledge like things in terms of zeros and ones, so it makes it a lot easier to go directly to like the lower level stuff.
That's right. And if you're in one, and I think adding to that would be in communication, there's no way to communicate many of those at once, at least not with kind of 2 wires. So like we have a format required where we can structure things in terms of zeros and ones. Why does hexadecimal exist? Yeah.
Binary.
To abbreviate binary, that's right, and abbreviate a specific part of binary, or it's the reason that base 16 is helpful for something. Let's do this line first. A 0 or 1 is a bit, yeah? 1, 0 or 1 is 1 bit. What's 8 bits? Yeah. What does hexadecimal make easy? Byte level math. You can represent bytes quickly.
Why would they just make it like base 8 then?
Because a lot of times I think it's still structured. It's still helpful to have it be base 16. One character really maps to 4 bits. Yeah. So now like one hexadecimal character is 4 bits, and that messages are usually structured in groups of 4. Yeah. Is it?
Decimal also used in like RGB a lot, just like colors in general, I feel like are always described
Yeah.
with hexadecimal.
I feel like there are lots of things use hexadecimal for various reasons. I've seen in mechatronics is useful because it represents 4 bits in one number, and you'll see that come up. Okay, so you guys know decimal. Convention for binary would be 2 to the 10 is equal to 10 base 2, and then you might see 0b to represent that you're looking at a binary number. So 0b 10 is decimal 2. Make sense? Binary to decimal conversion, that's not so bad. Decimal to binary is much harder. So like let's do 0b 110. Yeah.
6.
Nice. How did you know that?
The first one is 2 squared, and then the second one is 2 to the first, and you add those together.
That's right. 6 base 10. So hexadecimal, nice. So we do that one, we can just make sure you guys are tracking these. So 16 base 10 is the same thing as 10 base 16, which is the same convention there. And then 0x is used to represent you're looking at a hex number. So that's 0x defines that it's hex. How about this? That one's gonna be harder. Do you know what it is? Yeah,
165
that's right. How'd you get that?
times 16 plus 5.
Nice. Excellent. Okay, so that's just a little bit about what way numbers are represented. You'll see that around in data sheets and in our code, other things. So you might see the hex equivalent, you might see the binary equivalent, or you might see the decimal equivalent. And then it's really there's tons of online converters. So if I'm ever doing anything that involves conversion back and forth, there's tons of them. You can just find them online. That's a link to one there. But you'll convert hex to decimal or binary to decimal and back. Okay. Now we're talking about digital communication. So this is key. If you're creating a robot, these robots have to have sensors and actuators, things that communicate with each other. A lot of engineers find this part to be very boring. I actually find it to be very exciting. I really like the digital communication part and debugging digital communication. I think it's fun. But it's really, really important because all robots have to do this. So there's some infrastructure around around these concepts that you'll find, some common vocabulary, but also like you would have to do this as part of building any robot. There's lots of options for digital communication, as we've kind of seen in other things. There's many different ways to do this. We're going to talk about two. The first is integrated circuit bus. I2C or I2C. So that's a communication bus called I2C or I2C, integrated circuit communication. Next is serial peripheral interface called SPI or sometimes SPI. And then another example would be USB, but we're not going to learn that. Usually, I think always, a bus will consist of a data line or lines, so some way to communicate data, and a clock. Data line and a clock line that communicate information and timing. Different sensors, so if you have your Raspberry Pi, for example, different sensors or actuators or whatever you're building with, they need to know that they're being communicated with. So some way they have to learn, okay, I'm being talked to, somebody's asking me for a value right now, I need to be prepared to send that value. Buses handle this differently, so we're going to discuss these differently, starting with I2C. I2C has 4 wires. It has SDA, which is data, SCL, which is clock, and then power and ground. Four wires, clock, data, power, ground. The way that I2C handles communicating with different chips is by addressing them. This is an example, not just of what I2C looks like, but sort of what digital communication looks like in general. And so I put this here. So SDA and SCL, those are the specific names for I2C lines. Other buses have different names of their pins. So if you see SDA and SCL, that's definitively I2C. And this is saying SDA has this kind of like the top one. The reason why they're crisscrossing is that's the data line. Those bits could be up or down. It's just sort of showing that's the timing of the bits. And what this is saying is kind of the next line is the clock line. So the clock line is just going up and down. It's separating the bits. In an I2C system, there doesn't have to be an agreed upon speed of communication. It's set by the clock line. Other bus communication protocols would sometimes require an agreed upon communication speed. We're going to talk at this bit rate. I2C doesn't do that, it uses the clock line. And when it sends a message, it's going to structure that message. The message will include the address of the chip being spoken to, and then some other information we'll talk about in a second. Chips are identified by their address. Okay, yeah.
Can you change a chip's address easily?
Yeah, so let me think. Okay, so yeah, I'm going to talk about that right here. So each sensor or chip on an I2C bus is provided an address during manufacturing. It's sort of set up in the chip itself. And usually chips will have a pin that have a default address, so something like 0x, 02 or 0x05. So it'll have a default address, and then you can typically adjust that address by applying a voltage to a pin of some kind described in the data sheet. So you can change their address, but usually not by much. So you couldn't have 255 of the same chip. that usually wouldn't work unless there's a different way to change that address. But you can usually have more than one. Okay, so the way I2C works, every chip on the bus has an address and they're spoken to just like a neighborhood. Every kind of chip is addressed by name and it knows it's being communicated with. So the address is usually set in hardware. So that means it's default, it's part of the chip itself, and you can change its address, but in hardware, changing a pin configuration. Sometimes there are a few options. In this type of communication in I2C, they use the term controller and responder, which replaces master and slave. So some of the naming conventions still use master and slave. That's being changed by IEEE, I think, and others. So I've tried to use controller and responder. So in I2C, there can be multiple controllers and multiple responders. But let's think about a communication of a message. Then all of this information is defined in a message. Here's an example of a message. The first thing it's going to send is its 8-bit address. So this basically it toggles the bus. So it knows somebody's speaking, then it sends an address. Everyone's listening on the bus, they all listen to that address and they understand if they're being spoken to. So the first thing it sends is this address. Then the next thing it sends is something called an operational code. So that code's going to tell it something, like what's happening, like what is the intent. Usually it's to either provide a value that's going to be put in a register, or it's to receive a value that's going to be put in a register. So it's usually saying, what information am I about to send or receive? And then this is usually the data. So then there's going to be some data payload. Yeah.
Is this like kind of similar to like just publishing and subscribing in ROS or something? Like
I
at a
don't-
very high level, or
I don't use ROS. So how does it work in ROS?
well, like you have like different like messages that are like contain data, and like I guess here like you have like topics in ROS that like you'll like kind of publish some data to a topic, and then you could have like another node that's like subscribing to that topic and like pulling that data.
Yeah.
So I guess like it's just like sending and receiving.
It's very similar to that. And that's probably built on some infrastructure of some kind. But this is essentially those are both just sounds like thoughtful ways to exchange data between integrated circuits. And someone, luckily, in the last 20, 30 years, has put a lot of time and effort into this, which we get to use, and it's actually like pretty turnkey. Most of these things you can just buy them and use them, like use the drivers, and everything works. Both for these buses and other buses like ROS. Yeah.
So, is the data like not necessarily sent by the controller? Like if the internal register thing like tells the responder to like provide data, so data is then sent by the responder to the controller?
Either like usually when a message is sent, it includes, let's say it's a request. There would be a message sent that includes send me the request information. Send me your value of this thing. Then that sensor would then respond with a message and then that data payload. That's kind of like how it works, and there can be multiple people asking and multiple people sending, not at one time, but in general. Does that make sense?
I was just wondering like how they prevent like devices from trying to talk at the same time.
They are all listening to they all have access to the bus and they know when it's like operational. Yeah, that's a part of it. All the information on the address, the message structure, the operational codes, where do you think you can find all that information? Yes. Okay. So I2C enables what's called multi-masters or multi-master or multiple controllers and multiple responders. So this I mentioned. Speed is regulated by what in I squared C? I said this like 2 slides ago or so. Clock. I squared C is what's called half duplex. Does anybody know what that means? Anybody old school telephone people? Nope. It means only one side can talk at a time. There's only one data line, so only one side can talk. So only one sensor can communicate at a time. And I squared C is, I'd say, older and slower than other buses that exist now, like CAN or SPI or USB. And it's mainly used for short distances. I'm going to say approximately 1 meter max. If you try to make them longer, then the capacitance in a line ends up choking the digital edge. Yeah.
Is I2C or why is I2C better than CAN bus, like a CAN communication?
I would say it's not better. A CAN is probably actually would be better,
Okay.
but it requires a CAN controller. So Raspberry Pis don't have CAN controllers. A lot of like hobbyist level integrated circuits don't have CAN. They're starting to have more of them are starting to have CAN.
So yeah, like it's like the Raspberry Pi, like CAN header and like the hat, excuse me.
Yeah,
I think, right?
There's a CAN hat for a Raspberry Pi. Yeah, so that's it. Just adds an extra layer of like hardware. Okay, so that's I squared C, just communication bus. You'll see it around. You're using it. Another bus is called SPI, the SPI or SPI, serial peripheral interface. It's a 5-wire bus or more. It's 5 plus, so it's going to be more than 5 wires. This is a diagram, kind of like the I squared C diagram. We have our controller here talking to the different peripherals. We're going responders. Everything is the same as I squared C, except a few important details. The data line is not called SDA, it's called MISO and MOSI. MISO is a data line. And it's master in, slave out. MOSI is a data line. It's master out, slave in. And then there's clock. So one thing that's different is now there's 2 data lines. So it's not just SDA like an I squared C, it's MISO and MOSI. That's one difference. And the other difference has to do with how chips are communicated with. In SPI, there are no addresses. Nothing is addressed. The way a chip knows that it's being communicated with is it gets a dedicated digital line to that chip that flags. It says, like, I'm talking to you. So that's called a chip select line. That's what CS0, CS1, CS2, ... That's a dedicated line. CS0 goes to the chip select line of the first IC. CS1 goes to the chip select line of the second sensor. CS2, third. So that means before it can communicate now, you have to send it a digital cue via the chip select line. SPI is what I'm saying, does not use addresses. Instead, it has a dedicated digital signal sent from the controller to all responders individually. Does that make sense? So that's how SPI just made a change. Instead of using addresses, they use a chip select line. I find this to be annoying because now it means I have to wire an extra wire from the controller to the responder. So, but it's a little more reliable and a little faster, or a lot faster than I2C. It also is full duplex. Why is it full duplex?
Because it has the 2 lines.
So it has 2 lines, yeah, so it can, the controller side can communicate and they can listen at the same time. So it's full duplex communication. And it only supports a single controller or master. So I2C can do multiple controllers, SPI only allows 1 controller. That's because someone has to manage all the chip select lines. So SPI only uses 1 controller. It's faster. Approximately 1 megabit per second. About 2x the speed of I2C, 2.5 times the speed of I2C. It was more recently developed. Okay, so for the next kind of like 20 minutes, do you have any questions about SPI or I2C or anything? That's kind of all I'm going to do on that communication / this quiz. Okay, so for the next 20 minutes, I want you to do your best to answer this, and I think like the less you look at the notes, the better. If you can do this without looking at your notes, that'd be very good. It's not hard, but it would just require you to synthesize that.